Hello, and thank you for joining us for our webinar, Green Solutions for Flash and Prep Chromatography. If you have any questions during the webinar, please utilize the Q&A function within Zoom. All questions will be answered at the end. This webinar will be recorded and a video will be made available in the next few days. Our presenter today is Josh Lovell, Application Chemist. As with many of you, Josh and I are both working from home. With that, I will turn it over to Josh.
Thanks, Sharon. I want to thank everybody for joining us today. If you guys have any questions, feel free to use the question and answer feature on the side there, and I'll try to answer them as they come up or at the end of the session. If I don't get to a question, I'll be following up with you afterwards. So I want to go ahead and get started then. So today we're going to be discussing green choices for chromatography, and specifically some green solutions for flash and prep chromatography. So the outline for today's talk is we're going to be discussing what considerations of green chemistry we can apply to chromatography, what impact can greener chromatography make, so if we make small changes, how they add up in the industry and how we can make a major contribution to the footprint, how we can be greener and how you can help. And specifically, we're going to focus on choosing your column, how the quality of your media dictates your capacity and your resolution, how that impacts your green impact, the importance of proper scaling for sample loading and column size. Changing your functionalization or media type can lead to different greener opportunities. We're also going to discuss some solvent system choices and alternatives to those. There's a pretty big drive to try and eliminate DCM usage because it's costly to get rid of, and it's a little bit more dangerous than some other chemicals and has more environmental impact. So we'll talk about some alternatives to the DCM. We'll also discuss some reverse phase alternatives to acetonitrile. And then finally, we're going to go into some specifics on how you can make your methods greener and more efficient and save you time and solvent. So I'm going to start with the 12 design principles behind green chemistry. One is in prevention. Next is atom economy, less hazardous chemical synthesis, designing safer chemicals, safer solvents and auxiliaries, design for energy efficiency, the use of renewable feedstocks, reduced derivatives, catalysis, design for degradation, real-time analysis of pollution for pollution prevention, and then inherently safer chemistry for accident prevention. And so we're going to kind of point out some of these specifics that could apply to, that we can apply in chromatography when we make some of these choices. So which of these are going to be principles that we can apply to chromatography? So prevention is something that we can address by minimizing waste, less hazardous chemical synthesis, so minimizing the use and amount of toxic substances, designing safer chemicals so we can design safer processes, safer solvents and safer auxiliaries, so solvent choice. Another principle from green engineering is design for energy efficiency. And so to maximize your efficiency, you meet your need and minimize your excess. This can be applied to our purifications as far as being efficient. So we're going to discuss this really in depth in regards to scaling. The use of renewable feedstocks. So as newer renewable feedstocks are implemented, how can we use these new solvent options and make them more readily used? And then inherently safer chemistry for accident prevention. So what kind of safety features and our purification equipment can be useful to help minimize exposure. The question is you know, on a small lab scale, what kind of impact can we have in helping chromatography go green for flash and prep chromatography? And so if we look at the E factors, which is the kilograms of waste per kilograms of product, you know, 4 different industry sectors here: oil refining, bulk chemicals, fine chemicals, and pharmaceuticals. And the E factor, the amount of waste per kilogram of product, is much greater in the pharmaceutical industry because there's many more steps involved in the transformation of these chemicals. They're more refined. It also has the least amount of tonnage, but it does have the greatest E factor. So if we can address purifications in fine chemicals and pharmaceuticals, where chromatography is more common, we can reduce the E factor and address some of this tonnage that's being used. So the amount of chromatography waste generated per researcher is small compared to manufacturing or large-scale processes, but cumulatively, chromatography purifications have a substantial environmental footprint. Additionally, these small changes for users towards greener methods can help to substantially reduce the footprint. Also, as when things get upscaled at the manufacturing process, maybe these changes can be implemented at that point also and have a greater effect. Some estimates of solvent purification constituting 56% of the total material to manufacture an active pharmaceutical ingredient. So that's a pretty significant amount in the process there, and that makes sense based upon how much solvent we use in a single run versus how many milligrams of compound we're purifying. So we're going to discuss, next section here is going to discuss how we can be greener. So we're going to begin by discussing what greener chromatography looks like in the lab. So we could reduce solvent usage. We can do this using via more efficient methods, proper scaling to maximize your loading per run, turning unnecessary resolution in your chromatography into solvent and time savings. We can substitute with greener solvent choices would be another action we could take. We can decrease our column waste by using reusable columns, reverse phase methods. We can increase our column loading capacity by using a higher quality stationary phase. And more efficient methods can lead to more concentrated fraction collection, so you reduce the amount of solvent you need to evaporate off from your product. So if we look at our flash purification workflow, what steps can we make green choices, and what should we be considering? So really the first choice in a flash purification is you're choosing a column. Are you using a silica column? Are you using a smaller particle silica? And that kind of dictates what kind of mobile phase system you're in. Additionally, the quality of the stationary phase dictates sample loading amount. And this really runs into the proper scaling for your column. So are you maximizing the loading per run? How much compound am I purifying? If it's a large amount where you're going to be putting it onto a larger 120 gram or larger column, maybe just doing a 4 gram scouting run would be worth it, just to make sure that your method is as optimized as possible. How difficult is the separation? How much resolution is there between my compound and the impurities that I'm trying to separate it from? And if there is resolution, could you go ahead and run that compound or run on a smaller column? Or could you go ahead and load more sample to take advantage of that resolution? The next step would be choosing a mobile phase for your system. Which system would give the most efficient separation? Sorry, one sec. I'm trying to get the screen to show me the chat. It's not. There it is. Okay. Okay. Sorry. Is there a greener solvent available? And then which system gives me the most efficient separation? And finally, what we could, ultimately do. This takes a little bit more time, but it's something that can yield benefits and time savings later if you're doing multiple purifications of the same compound. Are you interested in one or multiple compounds for your purification? If you're only interested in one, we can really focus the purification around maximizing resolution around that compound. If you're interested in multiple compounds, then we need to, probably have a longer method, a longer gradient time so that we can separate those out. If we're focused on one compound, we could do a focus gradient for the target compound. And the question you're asking, is there any unnecessary resolution that allows me to shorten my method? So, do we really care if our compound comes out in the second third of the separation? Do we really care what happens to the compounds in the first half? So we could, jump up to a higher %V sooner and get those impurities off the column faster, even though they might be combined. Do I care about anything after my target compound elutes? For flash chromatography, we can set with our mass spec, we could set up a run to terminate on target. So once your target compound comes out, the run's going to go ahead and stop on its own. You can do this without a mass spec if you're doing the same run. You do your focus gradient range and then go ahead and end your run after you know when your compound comes out. So that's something you can do. And then maybe you're using reusable columns. So alternate stationary phases like the amine column or C18 or C18AQ. How do we get longevity out of those columns so we don't have to replace them as often? So we'll kind of discuss that a little bit too. What about for prep HPLC? So the workflow in general is very similar. You're choosing a column. We're in prep HPLC. Most of the time we're going to be in a reverse phase system, and you're probably using a C18 media, but other reverse phase medias are also common. So proper scaling again is going to come into play. How much compound am I purifying? How difficult is the separation? How much resolution is there between my compound and the impurities? The nice thing about prep HPLC is you can translate it from analytical HPLC data a lot easier. On the ACCUPrep, you could even run a 4.6 millimeter column and do a scouting run on that and then scale up to a larger column. Once you optimize that on the small scale, you guys can scale that up directly to a larger scale column, and your method's going to translate very well. Choosing mobile phase, you're probably already in reverse phase. So, you're in water methanol, water acetonitrile. Which system gives you the most efficient separation? Is there a greener solvent alternative available? Sometimes this comes into play with acetonitrile. Optimizing my method. Like I said before, for flash, I'm interested in one or multiple compounds. On the ACCUPrep, you could do a focus gradient for your target compound, and that'll save you time, and we'll illustrate that later. The same question, is there unnecessary resolution allowing me to shorten my method? And do I care about anything after my target compound elutes? And then finally, are you doing multiple injections or multiple runs of the same compound? This can dictate how long your method run will be. And you can have some savings for in between runs also. And then definitely important for prep HPLC columns is proper washing and conditioning the column for storage so you don't cause any damage to that, as those are more expensive. So let's go ahead and we're going to get into selecting a stationary phase for flash or HPLC. And so the green impact of column efficiency. So column efficiency basically is going to be affected by how well the column's packed, particle size. So smaller particle size is going to be more efficient column. Particle shape, spherical versus irregular particles. So spherical particles are going to pack better. This isn't really a question for prep HPLC columns because you're using smaller particles already. They're going to be using a higher grade media. But for flash, this is an important choice. Our ReadySep gold material has a spherical 20 to 40 micron particle. It offers twice the resolution power as our ReadySep, regular ReadySep material. And so, you can take advantage of this in a couple different ways. With twice the resolving power, you could go ahead and load twice the amount of compounds, so it's twice the loading capacity. And, or if your separation is very difficult, you can take advantage of the added resolution just inherently there by doing reduced loading. It also offers higher optimal flow rates. Increased loading allows you to use smaller columns. So ultimately, you're going to use less solvent. And solvent column cost savings and time savings for you. So we'll discuss this on the next slide, but here's like your general loading for the gold ReadySep. You could load up to 20% material on there. Well, on your traditional ReadySep, you'd be loading about 10%. If you're doing a really difficult separation, you'd want to be in the 1% range. So we're going to go back to one of the green engineering principles. Maximizing your efficiency, meet your need, and minimize excess. And so actually applying that in chromatography and purification, that would be choosing the smallest column that would provide an adequate separation. So higher quality silica provides superior separation and increases your loading capacity. And that would allow you to choose a smaller column versus using regular ReadySep material. So this leads to a reduction in your solvent use, time of separation, and cost savings. And also, it may allow you to do a scouting run before scaling up so that you can establish the actual loading amount for your unique separation. As we know, a lot of our compounds that we're purifying are all unique. Sometimes they're easily purified. There's not any impurities eluding around it. And other times, you've got very close similar compounds that maybe you're co-eluting with it where you need to really maximize your resolution. The other thing is that you can go ahead and verify and optimize your method that way. And this would apply to all methods. Being green can save you time and money too. So as an illustration of this, so if we were using our next gen, Combo Flash next gen 300 plus system or 100, just choosing which column I choose can have significant impact on my solvent savings. So if I'm using a regular ReadySep column, I would be in the 10% loading amount for my compound. And so if I had 2.4 grams of compound, I could choose a regular ReadySep column, 24 gram regular ReadySep, or I could choose a 12 gram gold column. Just using a default method, I would save about 190 milliliters of solvent by going to that smaller column. The savings are even more drastic as I increase the size of my compound loading. So I would save 270 milliliters by going from a 40 gram ReadySep to a 24 gram ReadySep gold column. And as you see, as I go, if I go down to a 220 gram column, so say I've got 22 grams of compound, I want to purify that on a regular ReadySep versus a ReadySep gold, I would be using 1.7 liters of solvent more per run. So as we get into these larger columns, you're starting to see some significant solvent savings for the purification. And so those will really add up over multiple purifications. This is in addition to the next gen solvent use. We optimized all the methods on there and reduced the solvent usage by 10 to 50% for some of the runs. So you can already see significant solvent savings in our default methods there because of the optimization on the system. Another way that we could make a stationary phase choice that would impact solvent selection is choosing an alternate stationary phase. So in this case, amines are notoriously difficult to separate on silica, and they require some unique solvent systems if you're purifying them on silica. Otherwise, you see streaking. Another alternative is to choose a functionalized column like the amine functionalized stationary phase. If I was to purify this mixture of nicotine and 1-methyl-benzimidazole on normal silica, if I were to run that with no modifier on a hexane ethyl acetate gradient, basically I get coelution of the peaks at the end of the run there. They basically come off at 70%, start coming off of the column about 70% ethyl acetate and hexane, and we don't get any separation. If we do the run, if you look at the TLC and you do the run in dichloromethane methanol, we can actually get some separation, but you get a lot of streaking for the second peak. And that's using an ammonium hydroxide modifier. Same thing with triethylamine there. It helps to move the peaks as a modifier, move it up the silica, but still you get a lot of streaking and some coelution there. So the chromatogram on the right there, like I said, the top one's with hexane ethyl acetate. If we do that same hexane ethyl acetate gradient on an amine column, we can actually get separation of compounds A and B fairly early in the separation. So we're not using dichloromethane. We are eluting it faster off the column, and we're getting separation. So the column volume, this would be done in about 9 column volumes versus the whole run. So just changing your stationary phase can make for a more efficient separation. You can move that compound so it elutes sooner and actually get some separation there. So this is a really good example of how we changed our stationary phase. It allowed us to avoid using dichloromethane. It also allowed us to do a simpler mobile phase system with hexane ethyl acetate. So the amine columns are really good choice out there for purification of amines. Another way we can go green, normal phase to reverse phase. So as we substitute water in for, some of our organic solvents, that's going to be a green choice for us. So significant reduction in organic solvent use. Traditionally, reverse phase is going to be a reusable column stationary phase. So you're able to reuse this column multiple times. Just be sure to follow the care instructions for reuse. Those get packed with the columns. The only problem with reverse phase is that you're going to have a little bit of a less loading capacity compared to the bare silica. So about 10% the capacity of bare silica due to functionalization. But it does allow you some different, definitely allows you different selectivities to optimize your purifications. So you can easily do multiple runs also with some of these systems, definitely on the PrEP HPLC system. You can do multiple injections of without any user interaction, basically. You can do multiple runs easily. So the next kind of major component of making green choices in our chromatography purifications is our mobile phase. So if you look at the solvent selection chart, so this groups solvents based upon their hydrogen donor, hydrogen accepting, and large dipole abilities. So you can see kind of group 1 there is your ethers, and group 2 is your alcohols, group 3 is your THFs and DMF. Group 4 some acids and glycols, and group 5 is DCM. Group 6, you start to run into ethyl acetate and acetone, acetonitrile. Group 7 are like your aromatics, and then group 8 is chloroform and water. So as these solvents are grouped together or get grouped into certain groups, they're going to have like properties. And so we can use this 2 ways. So, if you're using acetonitrile as a solvent. You could maybe use acetone or ethyl acetate instead. They would have similar properties. Another way you could look at this group is if you know you have a separation that doesn't work and you're using diethyl ether as a solvent maybe, or something, or MTBE, you could change to ethyl acetate or vice versa. You could go to a different group and see if you can get different selectivities. So there's kind of two ways to use this this table. It's kind of a nice guideline. Ultimately, though, one of the big solvents we're trying to reduce the use of is dichloromethane. It's a nonpolar solvent with really high dissolution power. So a lot of people like to use it for that reason. It's really good to help purify amines on silica. Is commonly where it's used with methanol and maybe with a modifier. However, it's toxic. It's difficult and costly to dispose of due to its low flammability. Some other solvents that are trying to be replaced and reduced are acetonitrile and THF. And these are traditional reverse phase solvents. Acetonitrile more so than THF, but people do use THF as an organic modifier. And this is due to their toxicity issues. And finally, hexane is one that we're also that you'll see is commonly being replaced with cyclohexane or heptane. And this is because of its volatility and its higher toxicity compared to heptane. So we're going to discuss some alternative solvents for these choices that may be useful for you guys in the lab. So we're going to begin with dichloromethane. So dichloromethane, there's a really neat paper in 2008 and 2012 there that described some different alternatives to DCM solvent systems, basically. So a lot of times we'll use DCM and methanol to purify some of these compounds. And so for neutral compounds, what this graph is showing here is that from 0 to 15% methanol and DCM, you're able to get similar purification by using a 3-to-1 ratio of ethyl acetate ethanol as your modifier in heptane. Although you're going from a gradient from 0 to 100%. So alternatively, you could also use just ethyl acetate, although that only gets you to about 10% of that methanol, or isopropanol. And then finally, another one is using MTBE as methyl tert-butyl ether as your base solvent, and then mixing that with the 3-to-1 ethyl acetate ethanol or methanol by itself. And you can get similar separations for these neutral compounds, this group of neutral compounds here. So the nice thing about the 3-to-1 ethyl acetate ethanol is it actually offers you a wider range of elution strength. So you can kind of fine tune your resolution a little bit further because you have a wider range that you can play with. When we are limited from 0 to 15% methanol, once you get to 15% methanol, everything is just really traveling down the column. There's not really a benefit to going above that. Especially if you're using basic modifier, you're going to start dissolving some of your silica. But these would be easy alternatives. It's now bought. You can actually purchase 3-to-1 ethyl acetate ethanol from Sigma Aldrich, or you could use isopropanol if you have that on site. But basically 100% ethyl acetate ethanol in heptane, well, I guess there's no heptane in there, but 100% ethanol, 100% 3-to-1 ethyl acetate to ethanol corresponds to about 15% methanol DCM. So you could run that gradient and get similar effect. And then I already mentioned the MTBE. Well, what about for basic compounds? So a lot of times these are amines we're trying to purify using DCM and methanol and maybe ammonium hydroxide or triethylamine. We can also do the same substitution here. So using heptanes as our base solvent, we could use a 3-to-1 ethyl acetate and ethanol with a 2% ammonium hydroxide modifier up to it. We can run this from 0 to 100% versus 0 to 15. The nice thing about, since we're not using methanol, is that we don't have to worry about going above 20 to 25% where we start to dissolve silica under basic conditions. This corresponds to about a 12% methanol DCM strength. So not quite as strong as the neutral, but it is a good alternative for you. You could also use MTBE, methyl tert-butyl ether, or ethyl acetate as the base solvent with methanol, ammonium hydroxide. So you can go up to 25%. Just be aware that when you use that basic methanol above 10 to 20%, depending on the basicity of the system, you can begin to dissolve your silica. And then the next class of compounds, your acidic compounds. So using an acid modifier with heptanes in the 3:1 ethyl acetate ethanol with up 2% acetic acid. We can basically run this from 0 to 90%, and it gives us basically corresponds to about 0 to 15% DCM methanol acetic acid. Same thing, we can use ethyl acetate or MTBE also as a base solvent, so instead of the heptanes. So we can change that base solvent, and it'll change some of our solubilities a little bit too, depending on your compound. So that would be dichloromethane alternatives. Another group of compounds that are starting to see more use, and this is a little bit more novel, is cyclopentyl methyl ether and 2-methyl THF. And so these are some common newer solvents, alternative solvents that are considered greener for normal phase or for liquid chromatography. The unique thing about them is that they're both from renewable feedstocks. So there's sustainable, and the cyclopentyl methyl ether may actually be a direct replacement for DCM. If you look at the table below in entries 1 and 2, you can see the RF range is very similar for those compounds in methanol, DCM, methanol CPME. Offers a very similar range for your RF. So for these compounds. This is actually seeing a lot of use in the purification of lipids, but there's a potential for more use in more traditional chromatography also. Same thing with 2-methyl THF here is also a possible replacement for DCM. It just kind of depends on your compounds. If you're trying to implement decreased DCM usage on site, there are some principles and guidelines and practices that were useful. If you're stocking ready-made solvent alternatives on site, and then also having TLC guides mounted near your instruments that helped guide change. Sites that did this saw reductions of up to 50% of DCM usage as they implemented these changes. So to help do that, you need to educate your users and provide them access to these chemicals. Reverse phase, we talked about acetonitrile and THF. Some examples, there's some examples of people using ethanol or acetone in place of acetonitrile and THF. 2-methyl THF, we discussed previously, would also be a suitable substitute for THF, and it comes from a renewable feedstock. Acetone is actually a stronger eluting solvent than acetonitrile, so less %B to move your compounds. It also would give you a little bit greater range. Obviously, the problem with acetone is that you run into some UV issues with it for detection. It starts to overlap with some of your compounds, and you're going to start to see baseline rise with it. So that's a problem. In reverse phase flash, though, on the next gen, we can run a system with our baseline correction feature on and be able to get rid of that baseline increase for acetone. I'll show an example of that. But this decreases the amount of organic solvent used in addition to replacement. The little bit of the problem with this is if you look at the back pressures for your prep HPLC, you'll see that acetonitrile is really nice because it lowers your back pressure. People can push flow rates that way. You're not going to be able to push the flow rates as high with acetone and methanol because your back pressures are going to increase a little bit more because of the viscosity. But acetone does kind of fit in between acetonitrile and methanol in that regard. For reverse phase flash, though, if we turn our baseline correction feature on, we're able to, we could do normal phase use of acetone. We could substitute acetone for ethyl acetate if we wanted to, but ethyl acetate's commonly used and not a problem generally. But we could replace the use of acetonitrile with acetone and use it in reverse phase. So water acetone mix here. You can see the baseline rise is not an issue. We're able to get clean elution of our peaks using acetone here. So at least for reverse phase flash with baseline correction, you're able to open up your toolbox a little bit more by being able to use some UV absorbing solvents. So finally, we're going to get into some method specific things and how can we make our methods greener. You know, we like to preach the impact of resolution on your separations and how that kind of gives you some different choices you can make in regards to optimizing your purification. So if we have adequate resolution or excess resolution, so we get baseline separation of our compounds or more, we can take advantage of it to be greener. So we can make a couple different choices there. If we have excess resolution, baseline separation, then we could maybe load more compound for that separation. Two, we could maybe scale down to a smaller column for that same separation if you don't have more compound to purify. Three, we could run a shorter separation over a focused range. And then you could also scale up from that also. Or four, you could just run it faster. You know, you could do a gold speed method instead of a gold resolution method. So there's a few choices. It kind of depends on what your priorities are, on which one of those you choose to make. So those would be kind of the choices you could make, and depending on what your priorities are, would lead you down a certain path. If you wanted to be greener, you know, I would increase my loading of my compound, or I would scale down to a smaller column. You know, you could shorten the gradient length, and that would save you solvent. So this last example, I wanted to show an example. On our ACCUPrep system, we have a focus gradient generator. It's really neat. It allows you to run a scouting run on our prep HPLC system on like a 4.6 millimeter column, and basically develop an optimized method after, you know, that's focused on your target compound. So essentially kind of how this works is on the right here is our scouting run on the ACCUPrep. It's a 4.6 millimeter column. We're just kind of trying to see where the compounds are coming out. We're not trying to separate them at this point. We're just trying to see where the compounds are coming out. It's basically an analytical run at this point. So once we determine where our compound of interest is coming out, and so we're interested in peak 1 here, we find that it comes out around 70% B. So basically, it's not even moving down the column. It's just sitting at the top of the column until you get to about 65% B. And then it starts to travel down the column. That's where we actually get separation, retention and separation. And then after that point, at about 85% B, it's off the column. So if you were to run a default gradient from 10 to 100% methanol and TFA, basically the compound is not moving during about probably 80% of that separation. It's either sitting at the top of the column or it's already off the column. So 80% of that separation, that gradient time, is wasted. So we could get really good resolution around this peak if we just run a 12-minute gradient versus the 20-minute 10 to 100% gradient. We run a 12-minute gradient from 65 to 75%. And we're going to get our compound that comes out basically in the middle of that gradient with much better resolution around our target compound. So this is a crude purine extract. We see the peak in the default gradient there at around 19 minutes. Comes out in 6 minutes with very good baseline resolution on the back end of it, and then slight impurities ahead of it. But that peak was co-eluting more in the default gradient. So we've increased our resolution around our target compound. We'd be able to scale up more on this, and we actually resolved it into multiple peaks there. To kind of quantify some of the savings there that you'd see, if you were to run a default method at this scale, you'd be running at about 0.8 liters per run. So it's on a 20 millimeter column. If you were to do successive purifications of that, if you factor in your equilibration and everything and washings, you'd be about 2 liters per run. So basically taking that compound and then repurifying it over the default gradient. Or you could have done the focus gradient. It would have taken you a little bit more time, but you would have used less solvent. So we would have done our analytical run at 1 milliminute, found out what the optimized method was using the focus gradient generator, and then scaled up directly from that. We would have used less solvent in that run. Now your savings you would really start to see is if you're doing multiple injections of this compound. So if say you have a large batch of compound, now you're going to start saving on each injection about 0.2 liters. And you're going to also start saving time at that point. So optimizing that method for multiple injections can really have significant benefits for you. Depending on the purification, you can get rid of the wash step. Basically, everything's going to kind of stay at the top of the column, and I should say all the stuff after your compound of interest is staying at the top of the column until you do that wash step. So you can do the wash step at the end of those runs. You could also do the focus gradient. Doing just the focus gradient run on its own offers you some savings. So when you start to do multiple injections of the same compounds, you can start to compound some of these savings. So what about my flash methods? This focus gradient seems great on prep. It's easy to implement. How can we do this on our flash system? So this is something we're trying to implement on our flash systems in the future, something we work on in the lab. Just to kind of illustrate this resolution advantage you get by doing a focus gradient though. So if you can do a focus gradient kind of over any range. So if your compound's just coming out in the first half of a separation, maybe you could run from 0 to 50%. Or if it's coming out in the back half of the separation, you could run from 50 to 100%. So this is an illustration of our default method, our gold resolution method, and then the focus gold resolution method. And using the default method for these two compounds, we get baseline separation. If we do a gold resolution method, which is slightly longer, sorry, this is on a gold column, sorry. The first one is on a regular ready set column. The second one's on a ready set gold column. So because of the added, because capacity and smaller particles for the ready step gold, we get better separation with the gold resolution method. We can see we get slightly better baseline resolution. If we focus that gradient from 25 to 35%, now we get about a minute's worth of resolution on either side of that peak. And now we can go ahead and load more compound and increase our loading based upon that. So this would be something where you would need to have an idea of where your compound's coming out. And you can narrow it over a range of even 20% and see savings or increased loading capacity for your separation. Finally, other ways you could be greener. If you're not using a reusable column, then if your compound elutes early in the method, you could shorten your run by stopping the run after elution. So if you purified this compound before, you know it comes out, you know, at 6 minutes, and you've got like a 12-minute default method, you could go ahead and, you know, get rid of everything after the 6-minute mark if you know your compound's already come out. The rest of the gradient's not necessary for your purposes because your compound's already off the column. The one thing you'd want to be sure of is that you let the run finish fraction collection of the peak, which is obviously delayed because of the tubing volume from the detector to the fraction collector. So, you know, just let it run for a few, about a half minute after the peak comes out or is done coming out. You could also take advantage of our end of run hold feature on the next gen. Basically, that allows you your run to stop. The column won't do the air purge until you tell it to do so after you've ensured that your compound's eluted off the column. So it'll basically pause the run and wait for you to say, okay, yeah, my compound's off, and then it'll go ahead and air purge the column and do all the wash steps and things like that for the valves. So in summary, some of the things we discussed today, the importance of chromatography towards green chemistry principles. We showed where green chemistry choices can be made in the flash and prep HPLC purification workflow. Presented how proper scaling can affect the reduction of overall solvent use. Showed some different solvent choices, including some green alternatives to DCM and acetonitrile. And then just demonstrated how the focus gradient generated on the ACCUPrep could save you solvent and time. Here's a summary of my references. This presentation will be available later, so you guys can look at this. There's a lot of really good information in these references in regards to chromatography and green chemistry, and some good guides on how to implement some of these changes in the industry. So I want to thank you guys for your time today. I'm going to go ahead and look through and see what kind of questions we have and see if we can get some of these questions answered for you guys. So let's see. Okay, so these, like I said, these slides will be available online and via video. One of the questions is using water affect the combo flash pumps or not? So this is not, the water is fine for the combo flash pumps. If you're going from normal phase to reverse phase on the next gen or any combo flash system, we have a tech note describing how to go from reverse phase to normal phase to ensure that you don't have an immiscible solvent like hexane in there when you're trying to flow water, to make sure that you flush all the flow paths with a intermediate solvent like IPA, isopropyl alcohol, which would be miscible with both hexane and water, is a good choice. So you want to use like an intermediate to go back between reverse phase and normal phase. We have a tech note regarding this. I can't remember the number off the top of my head, but you can, if you go to our website and search for normal phase to reverse phase combo flash, it should come up on there. And if not, you can always email us with questions. That's something that a lot of people do try to do on their systems. Other times, if they're doing a lot of reverse phase separations, they'll dedicate a system to just reverse phase, so you don't have to go back and forth. Another question. Could you provide an example of adequate resolution in terms of RF? So we talked about, so for flash chromatography, we like to work in column volumes, and you know, we like to say if it's within 1 CV or more, we can usually get good separation of it. In RF, 1 CV is about 0.1 difference, so CV is going to be 1 over the RF value, so 0.1 would be a RF value where you'd be able to get a decent separation. If that's larger, like 0.2, 0.3, that separation is going to be even easier. So if you can get above 0.1, you can usually get good separation on your column. Another good question is, when you're doing a scouting run, how much sample do you use and what type of column should you use? So when you're using the focus gradient feature on the ACCUPrep, we require you to use the same column media that you're using for your prep column. So you want to be sure that's matching, because if that column media is not matching, essentially you don't have you can't say that one media is alike to another versus different brands because of different chemistries and different selectivities. So that could lead you astray. So you need a matching chemistry between your media is one. And then sample amount, you know, that kind of depends on the, you know, each unique separation. But, you know, we could go down to, you know, 1 milligram per milliliter on the ACCUPrep and be able to see that. I suggest a little bit more. I like to work in the 10 milligram range and then scale up from that. So that's a possibility. Depends on how well your compounds are visible also. For the scouting runs on the prep system, you'd only be using liquid phase sample. If you did a scouting run on your, you know, say you ran it on a 4-gram column, I would suggest using a solid load cartridge, because that's going to help eliminate any traveling of your compound due to the solvent strength of your dissolution solvent. So if you can try to eliminate that aspect, it's going to scale up a lot easier. A few more questions here. Sorry, just reading them here. Yeah, so one of the questions is how to access focus gold resolution method in your next gen 300 plus. So basically just load the gold resolution method, the default method, and then you can go ahead and just change the gradient endpoint. So instead of running from 0 to 100%, change that from 10 to 30. So it's the same length. It's just over a focused range there. And then let's see here. There are any advantages to using triethylamine versus ammonium hydroxide in systems with ethyl acetate or ethanol and heptane systems for amines? Whenever I tried to purify amines, I always like to use triethylamine. It seemed to behave a little bit better. For these examples, they used ammonium hydroxide and didn't have any issues, it seemed like. So I'm not sure if one is better than another in this case. I do know that when I was purifying amines in graduate school that triethylamine was usually our go-to and seemed to have good success with that. You could use an amine TLC plate. We didn't show an example of that on there. We just used it in the column via the chromatogram. Okay, one more question here. For reverse phase purification, acetone was suggested, but could not be used if the fractions have to be lyophilized. Do you have any solutions for this? That's a good point. I mean, there's going to be cases where you're not able to substitute with acetone. And then, you know, so you're not going to be able to make some of these changes, you know, in some cases for some of your applications. Sometimes you're going to be stuck with what you're already using with acetonitrile or methanol or things like that, and you can't necessarily make the change. So it's going to be unique to your samples. So, so like I said, this video will be online. You guys will be able to see these references. You guys can look into them yourself. If you guys have any further questions, feel free to email me or email Teledyne. Appreciate your guys' time. Stay healthy and have a good rest of your week.
Thank you, Josh, and thank you all for attending our Green Solutions for Flash and Prep Chromatography webinar. It was recorded and a video will be made available. If you have any questions regarding this webinar, please feel free to reach out to me through Zoom and I'll forward it on to Josh. I can also provide certification of your attendance if desired. If you would like a certificate, please email me through Zoom and I'll get that prepared for you. Thank you again for joining us. Stay healthy and have a great rest of your day.